Electric motors, they're literally everywhere. They are the hidden engines of our modern world, silently powering pretty much everything around us. But have you ever stopped to actually think about how they work? How does plain old electricity get turned into powerful spinning motion? Well, let's dive in and uncover the secret behind the spin.
Yep, you probably guessed it, an electric motor. I mean, think about it. The blender in your kitchen, that toy car, even a massive electric train. They're all powered by the same fundamental idea. These devices are absolutely everywhere, turning electrical energy into the motion that makes our lives possible.
So at its core, that's all an electric motor is. Pretty simple, right? You feed electricity in one end, and at the other, you get a rotating shaft that can be connected to gears, fans, or wheels to do all sorts of useful work. The real magic, though, is in how that conversion happens, and it all starts with a totally invisible force.
Okay, so if you really want to understand an electric motor, you first have to get your head around the basic principles of magnetism. This is the force that we're going to harness to create motion.
You probably remember this from science class, right? It's a really simple set of rules. Every magnet has a north and a south pole. If you bring two opposite poles together, a north and a south, they pull towards each other. But if you bring two of the same poles together, like two north poles, they push each other away. This fundamental push and pull is the exact force we're going to use to create spin.
Now, permanent magnets are great, but they've got one big problem for us. They are always on. You can't just turn them off. To build a motor, we need a special kind of magnet, one that we can control completely, with the flick of a switch.
And what's really cool is how simple this actually is. You just take a regular old metal bolt, wrap it up tightly with some insulated wire, and then run an electric current through that wire from a battery. The flow of electricity forces all the little magnetic bits inside the bolt to line up, and bam, it instantly becomes a magnet.
And this gives us our first key component, the electromagnet. Unlike that magnet you've got on your fridge, we can turn this one on and off just by connecting or disconnecting the battery. But that's not even its most powerful trick, not by a long shot.
Okay, this right here is the secret ingredient for a motor. This is the game changer. If you reverse the flow of electricity, say by switching the wires on the battery, the north and south poles of the electromagnet instantly flip. So now we don't just have an on-off switch, we have a polarity switch, and that changes everything.
All right, now let's see how this all comes together. We've got our permanent magnets, and we've got our controllable electromagnet. It's time to put them together and generate that first critical push.
So what we'll do is place our electromagnet on an axle so it can spin freely, and we'll put it right between two permanent magnets. As soon as we turn the power on, the laws of magnetism just take over. The north pole of our electromagnet gets repelled by the outer north pole and attracted to the outer south pole, and that forces it to spin a quick half-turn to line up perfectly.
And just like that, it's stuck, dead in its tracks. The forces are perfectly balanced. The opposite poles are all lined up, and there's just no more reason for it to move. So we've created a single half spin, but that's not exactly continuous rotation, is it?
So this is the big engineering problem we have to solve. This is the central challenge of a simple DC motor. How do you give it that next push to keep the rotation going, over and over and over again?
Well, the solution is an incredibly clever little mechanical device that automatically flips the poles of our electromagnet at the perfect moment every single time.
It's called a commutator. So just picture a ring that's split in two with a little gap on each side. This ring spins right along with our coil. Then you have two stationary contacts called brushes that just slide along its surface, feeding it power. And because of those gaps in that ring, something amazing happens with every single half turn.
So here's what happens. As our coil is finishing its first half turn, the brushes are just about to cross those gaps in the commutator ring. At this very moment, the coil is almost perfectly aligned, and that magnetic force is just about to vanish.
And then, right at that instant, the brushes cross the gap and connect with the opposite segments of the commutator. This immediately reverses the current and flips the electromagnet's poles, so that north pole that was just being pulled in is now being pushed away, which forces the coil to keep spinning to try and align itself again. This brilliant little cycle repeats over and over, creating continuous rotation. It's genius!
So now that we have the basic concept down, let's take a look inside a real DC motor and learn the proper terminology for the parts we've just put together in our minds.
The stationary outer magnets, they're called the stator. Pretty easy to remember, it's stationary.
The whole rotating assembly in the middle, our electromagnet coil, is called the rotor because it rotates, or sometimes the armature. And of course, we have the commutator and the brushes, which work together to be that all-important automatic switch.
Now, our simple one-coil model works, but it does have a problem. The rotation would be pretty uneven and jerky. Even worse, it could get stuck in what's called a dead spot, where the brushes are right over the gaps in the commutator and they completely cut off the power.
Real motors solve this by just adding more coils to the armature and more segments to the commutator. This makes sure that at least one coil is always in the perfect position to get power and generate force, and the result is a much smoother, more continuous rotation. If you want to make it more powerful, you just add more wire wraps to each coil and supply more electricity.
This spinning force actually has a name. It's called torque. The more coils, the more wire, and the more electricity you use, the stronger the magnetic fields get, and the more torque the motor produces. And more torque just means a faster, more powerful spin.
And you know, this simple spinning motion is the foundation for almost every kind of mechanical task you can think of. Whether it's the simple spinning of a fan or a more complex mechanism like an electric knife that turns that rotation into a back and forth motion, it all starts right here with these basic principles of electromagnetism.
So the next time you hear the hum of a fan or a blender or even your computer, you'll know exactly what's going on inside. It's this elegant dance of magnets and electricity happening in there.